So today we'll start with the second lecture of gravitation. So before starting the chapter, there are some news. Okay, the application window for your JEE mains demonstration has already been opened. The last day of the application is 22nd November. Make sure you fill up your form before that date. Okay, means the registration plus. Make sure the application fee has been submitted before 22nd November. Okay, just don't go through the deadline. Just make it 2-3 days before the deadline. The last date is 22nd November. Okay, do not delay it, kind of thing. Okay, fair and fine. I'll briefly show you how to fill up the application form. Just open your browser. Okay, browser, open google.com and just type out IIT JEE application form. IIT JEE application form 2025, 2025. The first link that you see. Okay, just let me blur out. Let me blur out myself. Okay, the first link that you see would be the one. Some of you might get some sponsored link, but just read the site out here. Okay, the site might read jmain.nta.nic.in. That would be the official site. Okay, slash online application form and whatever the site out here. Okay, just click on the site. Okay, out here you'll get link to online form for JEE mains 2025 session 1. So just click out here. Okay, so when you click out here, will be redirected to this page. Now some of you might already have registered, some of you might already uh, be, some of you might already have been registered. Okay, to them just fill up your or upload your photos, not upload your photos, upload your documents, kind of thing. Submit out the fee. Okay, for those who haven't registered, okay, those who haven't registered, just enter the OTP that out here. Or those who haven't done anything, those who are just new or haven't even started filling out the application form. See, after coming out here, just enter the OTP out here. My OTP is 401 4091 S9 S9. Okay, and click on new registration. Those who haven't done anything up till now, just click out the this capture kind of thing and click on new registration. Okay, and there will find many options. Okay, gotcha. Out here we'll find a list of some details. The first list is the application fee kind of thing. Okay, application fee for different categories. For most of you, it's for male candidates is 1,000 rupees. Okay, for female candidates is 800 rupees. The rest are category wise. For general, it's for EWS and OBC, non-familiar, it's 800 and 800. Sorry, 900 and 800. SC, ST, PWD, and physically disabled, it's 500 and 500. Third gender, it's also 500. Okay, okay. And the second category is for Bachelor of Engineering, okay, BArch, Bachelor of Architecture, and Bachelor of Planning. Even those categories have been given. It's 2,000 and 16,000 for general, uh, EWS, OBC, NCL. EWS is nothing but economically weaker section. Okay, you have to have a certificate for that. Okay, and OBC, NCL, non-creamy. For them, the application fee is 2,000 for males and 1,600 for females. ST, ST, PWD, PWBD, for them the application fee is 1,000 and 1,000. So basically, the second part is not for you, kind of thing. The for those are planning for JEE main or BTech kind of thing from IITs and NIT. Just this part is for you. Okay, the first part is for you. Below, if you go down, you'll find some necessary thing. Achha, one more thing that will cause a lot of trouble is the getting the format of your photos correct. Okay, to get the formats of your photo correct, just open up Google again. Okay, in your browser, and just type photo resizer. Photo resizer. Okay, so image resizer.com. That is the first link. Just click out here. Okay, upload your photos or whatever photos you have from device. Let's select update. Okay, out here I'll just upload my signature. Okay, now this is my signature. Now some of you first have to crop it. Okay, so crop it accordingly. After the cropping has been done, just click on crop out here. Okay, and then resize. Resize means to whatever format. Generally for signature, the rule out here is given how much. Let's see. Okay, passport photo size from 10 KB to 300 KB. An image from signature should be from 10 KB to 50 KB. So out here, okay. So in the tab of image resizer, just come down out here, and out here it's given target file size option. Okay, just click out here whatever the desired target is, 50 KB. Okay, 50 KB and resize image. Okay, it will be lower than 50 KB or whatever. Because my original image was much more smaller, so I did not get the minimum threshold. But since most of you will be using CamScanner or any other file, just do it. Okay. So having said that, we'll go down out here. Okay, and just click on the confirmation box out here, the confirmation box, and click here to proceed. After proceeding, we'll have a list of forms. Okay, let's fill up the forms. Okay, And after filling out the form, submit, then you have to upload your photos, upload your signature, and upload your documents. And then you have to submit your application fee. Make sure you submit your application fee before 22nd November. Okay? Not delay, means not wait for the deadlines. Acha. The second good news that I'm going to give you is, okay, this was normal news. Okay? The application form has already been opened. Okay. The second good news that I'm going to give you is IIT Kanpur has just launched crash course for JEE aspirants. Okay, it's free, absolutely free. All you have to do is go to your browser, okay, go to your browser, open google.com. It's a 45-day course kind of thing, and just type out, wait, okay, just type out Sathi dot, not Sathi, SATHEE, Sathi IIT Kanpur. Okay, it's the initiative of IIT Kanpur. Sathi IIT Kanpur. Okay, from there you'll find out the first link. Okay, Sathi IIT Kanpur, and here we'll start with your this crash course kind of thing. Okay, just click on engineering, just get yourself registered and start learning. Okay, and they also have doubt sessions kind of thing. Just enroll out here. Just enroll out here and okay. Hmm. And just go through the lectures. Okay. Achha, these are the long format lectures. I'll give you, but let me see. These are the long format lectures. Okay. Hmm. Achha. And they also have live doubt clearing session. You can, achha. Okay. They also have live doubt clearing session out here. Okay. You can just Zoom call them and they'll respond to you somehow. Okay. And that's it. So these are our news for JEE aspirants kind of thing. Now I'll get back to our topic. Okay. Yeah. Achha, one more thing. If you all have any doubts kind of thing, just mention your doubt in the comment section kind of thing. Mention your doubt in the comment section means most of you are looking for contacts or personal contacts. I refrain from giving out my personal contacts due to some issues. Just make sure you give your comment out there. I'll try my level best to clarify your doubts. Okay. Just don't type just don't make abstract comments. I want to get in contact with you or I need your some help. Just type out the point at which you need my help kind of thing. If you need a help with gravitation, which chapter of gravitation? Okay, or if you need a help with some questions, which chapter of questions? When I'm free or when I'm done with my thing, okay, I'll just respond to your doubt. Okay. And if I'm not responding, that means I'm a little bit occupied. Okay. So having said that, let's start with the chapter of gravitation. Okay. So my workout here is done. Let's start with the chapters. Okay. This is the lecture 2. What happened? Okay. Okay. This is the lecture 2. Okay. Okay. So let's do a recap of things we have studied. First, we have studied about gravitation, then mutually uh, attractive forces. After that, we have studied something about the first question. Okay. Orbital mechanics, the center of mass means if two equal masses or if two relatively equal masses are there, this the center of the orbit would be the center of mass of the system. Okay. Then that's a calculation. Then we studied something about what? Acha, distance, Kepler's law. Kepler's law is nothing but the thing that we did. T square is directly proportional to r cube. Okay. And then we studied something about elliptical orbit. Okay. Elliptical orbit, see, one thing. Elliptical orbit is little bit complex. Okay. So first I'll give you the jugaad kind of thing, or first I'll give you the technique kind of thing, or first I'll give the simplified formula. Okay. Then later on I'll do the derivation. Don't go through both the things simultaneously, you'll get very confused because elliptical orbit is little bit unintuitive in nature. Okay. So the first technique is convert the elliptical orbit into circular orbit. The time period of the orbit is nothing but average of minimum radius from the sun plus maximum radius from the sun divided by 2, which is also nothing but the semi-major axis, isn't it? So for time period, we have to find out the time period for a circular orbit. Just make the radius of the circular orbit the semi-major axis, or average of minimum radius plus maximum radius divided by 2. Okay. So in this lecture, we'll learn something about angular momentum in an elliptical orbit. Okay. The angular, how do we find out the angular momentum? Not how do we find out, what is the formula for angular momentum in an elliptical orbit? And one more thing, the velocity of the planet at each point in the elliptical orbit. Okay. These are the two things. After that, what I'll do is, after that, I'll start with the derivation. Why? Because once you get into the derivation, okay, things are going to get a little bit complex. So first I'll give you the simplified formula that you have to remember, and then I'll start with the derivation. That much is clear. Okay. So this one, okay, elliptical orbit, or how satellites are launched. Okay. Value of eccentricity is nothing but c by a. Okay. If c is equals to 0, that means what? This ellipse is nothing but a circle. Okay. Okay. So e is equals to 1, not c. If e is equals to 0, that means this ellipse is nothing but a circle. Okay. Out it. The easiest way to solve for elliptical orbit is convert the elliptical orbit into a circular orbit where the radius of the circular orbit is a. Okay. And using this method or using this jugaad, I have only found out what? I have only found out time period. Okay. Time period of an elliptical orbit. Okay. Okay. Then we solve few more questions. So we proceed on with the next question from irodov. Okay. So in this question, well, let's see the question. Yeah. In this question, these are solar system. Okay. And in our solar system, the volume or the size of every planet and every sun has been reduced by a factor of n. That means if the value of n is 2, the size of the solar system has been halved. Okay, if the value of n is 4, the size of the solar system is quartered. Okay, so compare our two solar system: original solar system, reduced solar system by a factor of n. Reduced solar system by a factor of n. By a factor of n. Okay, if the value of n is 2, the size of the solar system will become half. If the value of n is 3, the size of the solar system will become 1/3. Okay, the question is asking if the density of each of the masses in the solar system was as it is. Okay, what would be the new time period, or what would be the new orbital time period of our new solar system that has been reduced in size by a factor of n? That is our question. Okay, so if the density, okay, of every material in the solar system is same, what would be the orbital time period of the new reduced solar system? Okay, so let's compare with any planet. Let's compare with Earth. Okay, so in our original solar system, this was the sun, isn't it? Okay, now what would be the mass of the sun in our reduced solar system? See, okay, what are we reducing? Are we reducing the mass? No, we are reducing the size. Okay, in this question, the model of solar system is scaled down by a ratio of n, keeping the density constant. That means you are not reducing the mass by a factor of n. You are reducing the size by a factor of n, keeping the density constant. Okay, that means if the original mass of the sun is ms, okay, let's say the volume or the radius, let's say the volume of the sun would be, or the radius of the sun would be rs. Okay, rs, radius of sun. Now, if the radius of sun has been scaled down by a factor of n, what would be the new radius of sun out here? The new radius of sun would be rs by n, isn't it? So if the mass of sun out here was ms, what would be the mass of sun out here? This is our sun, and I'm interested in finding out the mass of the sun. Okay, can I say density is equals to mass by volume? Density is equals to mass by volume. Okay, so mass is equals to density into volume. So mass, or mass of sun, is equals to density of the sun into volume of the sun. Volume of a sphere is nothing but 4/3 pi rs cube. Okay, so what is the mass of our new sun? So mass of new sun, okay, mass of new sun is equals to same density. Why? Because the density of each of the object in our solar system remains same. Okay, same density into new volume. So what is the new volume? 4/3 pi r cube. What is the new radius of a reduced sun? Rn by n. That means if the factor of, or if the value of n is 2, the radius of the sun has been halved. If the factor of n is 4, the radius of the sun has been quartered. So what is the new volume of the sun? New volume is nothing but 4/3 pi into new radius of the sun. And new radius of the sun is nothing but rs by n. Okay, rs by n whole cube. And why is that? Because it is being scaled down by a factor of n. Okay, so mass of sun, or new mass of sun. Okay, new mass of sun is nothing but density. Okay, density into 4/3 pi into rs cube by n cube, where rs is nothing but original radius of the sun. So if I compare this term and this term, okay, mass of new sun is nothing but mass of old sun divided by n cube. See, this entire term except this n cube is nothing but the mass of old sun. So mass of new sun is nothing but mass of old sun divided by n cube. Okay, now in our original solar system there was Earth. Okay, ERTH. the mass of Earth was me. Okay. Similarly, out here, if the density of Earth remains same, the mass of Earth was me. Okay. In our reduced solar system, the mass of new Earth, okay, Earth new, mass of new Earth would be nothing but ms by n cube. So similarly, mass of new Earth will be nothing but mass of old Earth divided by n cube. Okay. So since the solar system is scaled down, if the distance between Sun and Earth was nothing but radius of orbit of Earth or one astronomical unit, okay, if the distance between Sun and Earth was RE, in our scale solar system, this is nothing but RE by N. The size of the solar system has been reduced by a factor of N. So the new size would be nothing but RE by N. Okay. Now the question is asking what is the time period of this planet or what is the time period of this Earth? Would the time period change if the solar system has been reduced by a factor of N? Let's find out. Okay. So my first question is what is the formula for time period? The formula for time period is nothing but, see our previous question, the formula for time period in a circular orbit. See, out here, until and unless the question says anything about eccentricity or any specific hint about elliptical orbit, just assume your orbit to be circular. Okay, so in the chapter of gravitation, until and unless it is mentioned, just assume your orbits to be circular. Okay, so for a circular orbit, what is the time period? 4 pi square into RE cube or radius of orbit cube divided by g into mass of sun. Okay, so time period is given by 4 pi radius of orbit cube divided by g into mass of sun. Okay. My new question out here is what is the new time period out here? Okay. What is the new time period out here? The new time period out here would be nothing but T new of Earth or time period of Earth in the scaled solar system is nothing but 4 pi. The radius out here. Okay. What is the new radius out here? RE by N. So new radius out here is nothing but RE by N cube. Okay, divided by G into what is the mass of the sun in scale solar system? It is nothing but original mass of the sun divided by how much? N cube. So the new mass of the sun in our scale solar system is nothing but original mass of sun divided by N cube. So original mass of sun divided by N cube. Okay. So this N cube and this N cube would get cancelled. So this N cube and this N cube is getting cancelled. So the time period of our new solar system or scaled down solar system is nothing but 4 pi RE cube by G into ms. Okay. Now compare these two values. Is the new time period, is the new time period and the old time period same? Of course it is. So this value and this value is same. So the time period of the solar system would not change even if it is reduced by a factor of n. Okay. Assuming the density of all the materials is kept constant. Okay. So out here the answer is the time period of all the objects in our solar system would not change if we scale down by a factor of n or scaled up by a factor of n. It doesn't matter. The value of n gets cancelled out. Okay. Okay. The two important things to note out here is we are not reducing the mass by n or volume by n. We are reducing the radius or size of everything. Okay. Or linear everything by a factor of n. The radius, distance between astronomical unit. So that has been reduced by a factor of n. So this was done. Next question or question number 1.204. Okay. So let's proceed on to the next question. So this is the second question. Okay. Let's see what it says. In the second part of the question, a double star system consists of two stars moving around the center of inertia. That means whenever there are comparable masses, this is star 1, okay, this is star 2. They'll rotate around the center of mass. Let this be the center of mass. So this star will move around this orbit. And this star or the second star will move around this orbit. Okay. Let the mass of the first star be m1, mass of the second star be m2. The question is saying find the distance between the components of the double star. That means find the distance or this distance. Okay, from distance between star 1 to star 2. If the total mass of the system is equals to m and the period of revolution is equals to t. Okay, that means m1 plus m2 is equals to capital M out here. So this m or it is given in the question that m is equals to m1 plus m2. See, first few things that you need to note out here. For a double star system or a multiple star system, okay, whenever they are rotating about the center of inertia, the time period of revolution of all the stars will be same. Okay, so the time taken by this planet to orbit around this center of mass will be equals to time taken by this planet or this sun around its center of mass. Okay, so time period of this orbit would be equals to time period of this orbit. And how do I know that? Simple mathematics. Okay, let this be center of mass, isn't it? The center of orbit of both the star will be the center of mass, isn't it? If this distance is r1 and this distance is r2, okay, Okay, this distance is r1, this distance is r2. We need to find out the value of r1 plus r2. Okay, so what I said is the time period of both the stars would be same. Fair and fine. Now, how do I solve this kind of problem? Okay, I need to find out this distance here, no? So let me do, or let me take my origin out here. Okay, see, one thing to note out here is the origin out here. Okay, my first origin out here. Okay, now let me apply what? Let me apply the motion of sun 2. Okay, let me apply the motion of sun 2, or circular motion of sun 2. Okay, for second sun, for sun number 2. Okay, mv square by r, mv square by r2, or centripetal force, m2v square by r2. Okay, v square is nothing but the velocity of the second sun. Okay, now some of you might ask, sir, why aren't you using this formula for time period? This formula for time period was taken for the assumption that the center of the planet body or the planet object is much heavier than the revolving object or object in orbit. But out here, that is not the scenario. Out here, both the planets are, or both the stars are comparable in mass. So they'll rotate about center of masses. So whenever you are using Kepler's law, okay, Kepler's law, make sure Kepler's law has an assumption that the parent body is much heavier than the orbiting body. So out here, m v square by r2, where v is nothing but the velocity of sun 2. Okay, is nothing but g mass of sun 2 into mass of sun 1, or m1 m2, m1 m2. Why, what is the distance between them? The distance between them is nothing but r1 plus r2 whole square, r1 plus r2 whole square. So this is our equation. But I do not need to find out the velocity. I need to find out the time period, the period of revolution t. And how do I find out the period of revolution? Time period is nothing but 2 pi r2 by v, isn't it? Or 2 pi by omega. 2 pi by omega. Let the velocity of the sun to be v2. So instead of writing v, I'll as in v2. Okay. So outer m v2 square by 2 and m 2 pi r2 by v2, or omega 2. Where omega 2 is nothing but the angular velocity of sun 2. So first we solve for velocity, then we substitute the velocity in this formula for time period. Fair and fine. So let's solve for velocity. m2 will get cancelled. Okay. What will remain out here is nothing but v2 square is equals to g m1 into r2 by r1 plus r2 whole square. Okay, fair and fine. Now if I see this equation, time period is equals to 2 pi r2 by v2. Okay, now see, in order to substitute this value of v2 out here, okay, I need to do something. I need to first square out this one. You can also substitute the value of v2 is equals to under root of g m1 r2 by this variable out here. But instead of using under root, I'll square out this term. Okay, so if I square out this term, both left hand side and right hand side, I'll get t square is equals to 4 pi square r2 whole square divided by v2 square, isn't it? And now this v2 square is nothing but this entire term gm1 r2 by r1 plus r2 whole square. So t square is nothing but 4 pi r2 square divided by, what is the value of v2? gm1 r2 by r1 plus r2 square. r1 plus r2 square will go at the top. Okay, so divided by r1 plus r2 whole square, no? And this r1 plus r2 whole square will move at the top. Okay, so I'm writing this entire thing at the top into r1 plus r2 whole square. Now this r2 square and r2 will get cancelled. So t square would be equals to 4 pi r2 into r1 plus r2 whole square divided by gm1. Okay. And now the time period, this time period was given by t. Okay. We need to find out the value of r1 plus r2. Find the total distance between the components of double star. That means we have to find out the distance between star 1 and star 2, or the value of r1 plus r2. So in this equation, if I have to find out the value of r1 plus r2, how do I do it? r1 plus r2 whole square is equals to t square into g m1 divided by 4 pi r2, isn't it? And if I just remove the square out here and out here, what do I get? r1 plus r2 is equals to under root of t square gm1 by 4 pi r2. Okay. Similarly, if you want to write it, see out here r square, see t square is nothing but the time period of sun 2. Time period of sun 2 and time period of sun 1 would be same. Okay, 4 pi r1. r1 is nothing but the radius of sun 1 divided by, sorry, m1. out here it is given T square G M1. M1 is nothing but the mass of Sun 1 divided by 4 pi R2. 4 pi into R2. And R2 is the radius of Sun 2. You can also write this formula as T square G M2. That means I'm writing in terms of mass 2 divided by 4 pi R1. Okay. Or R1 plus R2 is equals to T square G M2 divided by 4 pi R1. Okay. Now you might ask, sir, how did you get this formula? This formula is not given. How did you obtain this formula? See out here. I have applied this equation using this term, no, for star 1. Now for your homework, just apply the same equation using star 1. But the velocity of star 1 was v1. Then apply the formula for time period. We'll get this answer. Okay. So if you apply the formula for time period for star 1, you get this formula. If you apply the formula for star 2, you get this formula. And see, this point is the center of mass of both the stars, no? Okay. So if I consider my origin out here, can I say m1 into r1 is equals to m2 into r2? Center of mass minus m1 plus r1, sorry, minus m1 r1 plus m2 r2 divided by m1 plus m2 is equals to 0. So m1 r1 is equals to m2 r2. Okay. So m1 r1 is equals to m2 r2. Now from this equation I can get that m2 by r1 is equals to m1 by r2, or m1 by r2 is equals to m2 by r1. Okay. Why? Just cross multiply. No, m2 by r1 is equals to m1 by r2. Just cross multiply it and see m1 by r2. I'm substituting the value of m1 by r2 out here by m2 by r1. Both are the same thing. No, m1 by r2 is equals to m2 by r1. m1 by r2 is equals to m2 by r1, isn't it? Okay, understood. So these are the next question. These are the question 205. Okay, I will proceed on to the next question. So in this question, there are two masses. Okay, m1 and m2. m1 and m2. They are separated by distance r. The question is asking find out the gravitational potential energy of these two masses. Okay. Now what is potential energy? Potential energy is nothing but negative of work done by conservative force, isn't it? Or work done against a conservative force. That is what is potential energy. Okay. So my first intuition is, what is the force out here? The force out here is nothing but F is equals to G m1 m2 by r square, isn't it? And work done by this gravitational force is nothing but F dot dr. Okay. Or work done by this gravitational force is nothing but G into m1 m2 by r square into dr. Okay. So when I integrate this one, okay, m1 m2 by r square here, so it is nothing but F is equals to G m1 m2. This 1 by r square can be written as r to the power minus 2, r to the power minus 2 dr. Now when I integrate r to the power minus 2 dr, I get r to the power minus 2 plus 1 divided by minus 2 plus 1. So when I integrate r to the power minus 2 dr, what do I get? R to the power minus 2 plus 1 divided by minus 2 plus 1. Okay. Now you can either apply definite integral or indefinite integral. Okay. If you are applying for definite integral, you put out the limits, upper limits and lower limits. If you are putting out indefinite integral, put out plus some constant and find out the boundary condition. This is the boundary condition. At r is equals to infinity, potential energy is equals to 0. Then solve for this one. Okay. So when I integrate, one more thing. Out here, force is not equals to this value. Work done. I'm solving for work done. No. So just work done is equals to G m1 m2 by this value. But if I solve for this value, r to the power minus 2 plus 1 is nothing but minus 1. Minus 1. Okay. Now here minus 2 plus 1 is nothing but minus 1. Minus 1. Now I can send this minus 1 outside. No, I can send the constant outside. So after if I send this minus 1 outside, the integral term becomes minus 1 or minus Gm1 m2 by r to the power minus 1. R to the power minus 1 can be written as 1 by r. 1 by r. Okay. So work done by the gravitational force is nothing but minus G m1 m2 1 by r. Okay. Fair and fine. Now, if you see something is weird out here or something is wrong out here, what is wrong out here? See, if gravitational force is acting towards left and my displacement is also towards left, the work done is positive, no? So in gravitational force, the work done is positive, isn't it? Because displacement is acting in the direction of force. Okay, but out here work done is coming as negative. What is happening out here? See, gravitational potential energy is nothing but work done by a field or work done by mass in bringing an object from infinity to that point. So you have done this in class. So at infinity, the direction is of force is attractive, and if it is coming towards the object, that work done is same as the direction as, see, the displacement is same as the direction of force, isn't it? So the work done should be positive, but out here my work done is coming as negative. What is happening out here? Potential energy or gravitational potential energy is nothing but work done in bringing a charge, work done in bringing a mass from infinity to that point in space. Okay, so my initial point would be infinity, my final point would be this point in space. Okay, so work done in bringing this mass m2 from infinity to this point is nothing but minus g m1 m2 by 1 by r minus 1 by infinity. 1 by infinity is already 0, so work done is equals to minus g m1 m2 by r. Okay, the wrong thing out here is this minus sign. Okay, because at infinity the direction of force would be this side, the displacement would also be this side, no, to arrive at r. So the work done should be positive, but my equation gives me a negative value. Okay, so what is happening out here? See, just note one thing: attractive forces are negative in nature and repulsive forces are positive in nature. Okay, attractive forces are negative, forces are negative, and repulsive forces are positive. And repulsive forces are positive. Okay, so what kind of logic is this, or how you derive at this point, or what is the logic behind this point or this sentence? See, first we'll solve the equation again by using this sentence. Okay, and then I'll give you the logic behind this sentence. Okay, so let's take this sentence as true. Okay, so this force or gravitational force are always attractive in nature. So out here I'll put out minus. Okay, so this minus goes out here minus. Okay, so this minus multiplied by the minus from integration becomes plus. So out here work done is plus, out here work done is plus, and out here also work done is plus. So work done by for bringing a mass from infinity to this point is nothing but plus g m1 m2 by r. Okay, so this much is understood, and this is, if you observe it, this is correct also. Okay, from infinity, if you are bringing this mass m2 from infinity to this point, the direction of force at infinity will always be in this direction or along the direction of displacement, isn't it? So work done is positive, fair and right. But to make this work done positive, I have this much sentence or this sentence. Okay, so the potential energy is nothing but negative of work done, or potential energy is nothing but minus g m1 m2 by r. Even this is true. Okay, so we found out the first part of the question. The potential energy of this system m1 m2 separated by distance r is nothing but minus g m1 m2 by r. Okay, now what I'm trying to say is, I'm trying to demonstrate that how this sentence, or how this what is the logical conclusion behind this sentence. Okay, attractive forces are negative and repulsive forces are positive. Okay, so let me write the sentence: attractive forces are negative, attractive forces are negative, and repulsive forces are positive. Repulsive forces are positive. Okay, in case of uh, non-contact force, or this non-contact force. Okay, now the logic behind this statement is nothing but, see, this is mass m1, this is mass m2, this is the separation between them. Okay, if you observe the force F, out here, F is equals to g m1 m2 by r square, isn't it? Now if you observe something out here, this force on the left hand side is a vector quantity, whereas on the right hand side g is a scalar constant, m1 m2 are masses, which is a scalar quantity. R itself is a vector quantity, but when you square a vector quantity, it becomes a scalar quantity. So what is happening out here? Okay, so to write the formula properly, we introduce a unit vector, or we multiply the right hand side by a unit vector. Okay, and that unit vector is unit vector of r. That means what? The direction of gravitational force will always be along the direction of r. Okay, now how do I give a sense of this r? That means along this line, it can go towards right also, it can go towards left also. So see, everything that we study in physics is studied in a coordinate system or a graph paper. So suppose this system, I'm looking at it from origin out here. This is my origin. Okay, when I'm calculating the force for body 2, the sense of r vector for body 2 is along this direction. This is r2. Okay, because body 1 is applying a gravitational force on body 2, and when I'm studying body 1, okay, the r vector comes from body 2 to body 1, or r1 comes from body 2 to body 1. Okay, body 2 to body 1. This is R1. Okay. So force on mass M2. Therefore, when I want to study force on mass 2 is nothing but force vector is nothing but G M1 M2 by R2 square into R2 vector. Similarly, force on mass M1. Okay, we have to study the force on mass M1. Force on mass 1 is nothing but F is equals to G M1 M2 by R1 square into R1 unit vector, isn't it? So this is the vector forms of gravitational law. Okay, vector form of gravitational law. So from here, the sentence of attractive forces are negative and repulsive forces are positive. I might ask, I still didn't understand. R1 is going from, sorry, R2 is going from 1 to 2. R1 is going from 2 to 1. So how does this thing justify? See, the direction of R2 is along this direction. If you take the formula as it is, the direction of force should be along the direction of R2, no? Because the only unit vector that is giving direction to this parameter or to this equation is nothing but R2 unit vector, and R2 unit vector is also towards right. So if anything that is towards right is positive, force is actually acting in the opposite direction, no? So to rectify this one, what we do is we introduce a minus out here. Understood? Now if you check, okay, F is equals to Gm1 M2 by R2 square. This up till here is a scalar quantity into R2 unit vector that goes from left to right. Okay, and if I have to find out the force, I have to multiply the unit of R2 vector by -1. So the force will be opposite to the direction of R2 vector. Okay. Now you might ask, sir, instead of R2 vector, if I want to write down the entire thing in vector quantities, how do I do it? See, there is a coordinate system. Okay, and in this coordinate system, this mass M1 will have a position vector. Okay, so suppose the position vector of mass M1 is nothing but, let's say, C1, not C1. Let's assign any other value. Okay, see, we usually assign R, but since I've already used R1 and R2, let's assign the position vector of M1 in this coordinate system or from the origin is nothing but, let's say X1. Okay, similarly, the position vector of particle 2 from the origin or mass 2 from the origin can be given as X2. Now, how do I write R1 and R2 in terms of X1 and X2? See, if you see these vectors properly, position vector is X1, position vector of mass M2 is X2. Okay, see this X1 and X2 properly. Can I say X1 plus R2, X1 vector plus R2 vector is equals to R1 vector? So X1 vector plus R2 vector is equals to R1 vector, or R2 vector, sorry, X1 vector plus R2 vector is equals to X1 or X2 vector, not R1 vector, X2 vector. X1 vector plus R2 vector is equals to X2 vector. X1 vector plus R2 vector is equals to X2 vector. So instead of using R1, write X2. I made a mistake out. Okay, X2 vector. X1 vector plus R2 vector is equals to X2 vector. Is equals to X2 vector. Okay, so from this equation I can write R2 as X2 vector minus X1 vector, isn't it? Okay, and how do I write unit vector? Unit vector can be represented as vector divided by magnitude of the vector. So this unit vector can be written as vector or R vector divided by magnitude of this vector, or it can be written as X2 vector minus X1 vector, which is nothing but the R vector, isn't it? R vector can be written as X2 minus X1. R vector can be written as X2 minus X1 divided by magnitude of R vector is nothing but X2 vector minus X1 vector, isn't it? Okay, so the gravitational force out here would be nothing but F is equals to minus G M1 M2 by how much? X2 minus X1 square into X2 minus X1, X2 minus X1 divided by X2 minus X1. Okay, this is the magnitude. Understood? So this is the vector form of gravitational law. Okay. Now some of you might have questions. This scenario is also related to question number 2 from electrostatics. Just read the question 2 of electrostatics from the chapter of electrostatics. Okay. Okay. Now, how does this fundamental work for electrostatics? Okay, that attractive forces are negative and repulsive forces are positive. So similarly, when I apply the same concept out here, to electrostatics, what happens is, suppose two charges are there, okay, Q1 and Q2, okay, they're separated by distance r. Okay. Similarly, for Q2, the direction of r vector would be from Q1 to Q2, isn't it? For Q2, the direction of r vector would be from Q1 to Q2. Similarly, for Q1, this would be the direction of R1, isn't it? Okay. Now, if Q1 and Q2, okay, both are positive, so force out here would be in this direction, force out here would be in this direction. Okay. So forces is equals to K Q1 Q2 by R square into R of unit vector. Out here, is there a minus? Okay, it depends upon the nature of charge. If both the charges are equal in nature, that means negative negative for positive positive, out here the formula will be as it is. Okay, out here the direction of R2 unit vector or R vector is along the direction of force for electrostatics. Okay, now see what happens if one of the charges are opposite in nature, plus Q1 minus Q2. Okay, R. Similarly, the R2 vector would go from charge 1 to charge 2. R1 vector would go from charge 2 to charge 1, isn't it? So force out here is nothing but K Q1 Q2 by R square into R vector. Out here, since the nature of charge 2 is negative, so multiply the Q2 by negative or minus Q2. And when you bring this charge or when you bring this minus outside, it becomes F is equals to minus K Q1 Q2 by R square into R vector. Understood? Now see, out here Q1 is, the force of Q1 is this side, the force of Q2 is this side. So the force of Q2 is opposite to the direction of R2, the force of Q1 is opposite to the direction of R1. That is why the minus of the charge comes outside. Understood? Okay. In case of like charges, the charges will remain as it is, and the direction of force will be along the direction of R. And that is why attractive forces are negative in nature, attractive forces are negative in nature, and repulsive forces are positive in nature. Okay, attractive forces are negative in nature and repulsive forces are positive in nature. We have done the same question in electrostatics. Okay, read the question of electrostatics from irodov, question number 3 or question number 2. So basically what these formulas are nothing but vector forms of these formulas. This is the original formula. Okay, original formula that we use in physics. But to simplify it, so that this formula is very complex, no? To simplify it, we use the shorter formula, simplified formula, and have the sense of direction by one logic. Okay, just apply logic and find out the sense of direction instead of going through all the formulas. Okay, and if you want to avoid this entire thing altogether, just remember attractive forces are negative in nature and repulsive forces are positive. This is the only sentence you need to remember. Okay. Now, this was the question I was solving. Our potential energy between 2 points or 2 masses separated by distance r is nothing but minus g m1 m2 by r. Fair and fine. Now, part B of the question. Okay, part B of the question is asking if mass m and a rod of length L, okay, there is a rod of length L, the mass of this rod is m. The mass of this rod is m. The distance between the mass and the rod, starting of the rod, is a. Okay, we have to find out the force of interaction between these masses and the potential energy of the system. So let's start with force of interaction, because in order to find out the potential energy, we have to do negative of work done by the conservative force, isn't it? So if I first find out the force and multiply that force into dr by negative value, I'll get the potential energy, isn't it? So first part of the problem will solve for force of interaction. Okay, force of interaction. Okay, now you get the intuition that we have to do some kind of integration of it. Okay, some kind of integration is inevitable out here. Okay, see, out here the gravitational force will be very different from the gravitational force out here. So in order to do integration, we have to take an element. Let's take an elemental mass. Okay, dm out here. The length of this strip is dx. Okay, or the thickness of this strip is dx. Okay, and this dx strip is situated at distance x from the mass m. Okay, so my first question is, what is the gravitational force between this elemental strip and this mass m? What I did out here is I took an elemental strip, isn't it? And now what I'm asking is, is an elemental strip of thickness dx, mass dm, separated by distance x. Separated by distance x. Okay. What is the force of interaction between these two masses? Force of interaction is nothing but g mass m into dm by x square, isn't it? Okay. This is the force of interaction, no? Now you have to somehow see the question out here is solved. Somehow you have to put this dm in terms of x and solve out the value. Okay. Now in order to convert this dm in terms of dx, can I say the density of this rod is same, or density of this rod throughout the rod is same? Okay. So if the density of this rod is same, or linear density of the rod is same, can I say mass of the entire rod divided by length of the entire rod is equals to mass of the entire rod divided by length of the entire rod is what? Linear density, isn't it? Should be equals to the density of this elemental strip. The density of this elemental strip, the mass of this elemental strip is dm, and the thickness of the elemental strip is dx, isn't it? So all I have said out here is the density of this entire rod is equals to the density of this elemental strip. Understood? So mass divided by length is density of this rod. dm divided by dx is nothing but density of this strip. So out here, can I do m by l into dx is equals to dm, isn't it? And if I substitute the value of dm out here, what do I get? Force is equals to gm into m by l dx by x square. Okay, this is the value of force. Acha, one more thing. Gravitational forces are negative. Attractive forces are negative. Okay. Now, if you solve for this one, F is equals to minus G M capital M by L into dx by x square. Okay, and when I integrate dx by x square, what do I get? F is equals to minus G small m capital M by L into x to the power minus 1 by minus 1. I can take this minus 1 outside. Okay, if I take this minus 1 outside, it will become plus, and x to the power minus 1 can be written as 1 by x. 1 by x. Now, what are the lower limits and upper limits? The lower limit is nothing but a, and the upper limit is nothing but a plus l, isn't it? The integration starts from here and ends up till here. So the lower limit of the rod starts from a, and the rod ends at a plus l. A plus l. So F is equals to GMM by L into 1 by a plus l minus 1 by a. Okay, or force is equals to GMM by L into how much? A minus L. If I take the LCM out here, it would be nothing but A into A plus L. A into A plus L. Okay. And if I subtract A minus L, or minus into A plus L, subtract this term from this term, no? Just take common LCM and cross multiply. We'll get this term. So F out here would be G small m capital M by L into minus L by A into A plus L. So out here L and A will get cancelled. Or F out here is nothing but minus Gm capital M by A into A plus L. So this is the force of interaction between a rod and a mass. So I found out the force of interaction. Now the second part of the question is asking find out the potential energy of the system. So in order to find out the potential energy, what do you have to do? For potential energy, you have to integrate the force with the earth, because potential energy is always a negative of what done by a conservative force. So potential energy potential energy of what? Of mass m and capital M of length L situated at distance a. Now my first question is order to find out the potential energy, I have to find out the force. So the force of interaction is nothing but this value. See, instead of using this value, I'll use this value. These and these are the same thing. I just simplify this term to become this term. This term is, however, easier to integrate. That is why I'll use this term. Okay. So force is equals to G capital small m capital M by L into 1 by A plus L minus 1 by A. So out here, force is equals to G small m capital M by L into 1 by A plus L minus 1 by A. Okay. This is L. This is the thing that I'm using. Okay. Or this is the term that I'm using, because this is easier to integrate. Then fine. Now what is work done? Work done is nothing but F dot dr. F dot dr. Okay. Out here, instead of using R, I'll use A, or F dot dA. Why? because the distance out here, distance between this mass M and capital M, instead of giving in terms of R, they are given in terms of A. So instead of using dr, I'll use dA. Understood? dA. So work done is equals to G small m capital M by L into 1 plus 1 by A plus L minus 1 by A minus 1 by A into dA. Okay. Now when I break these two terms, this can be written as work done is equals to G M capital M by L into 1 by A plus L dA minus 1 by A dA, isn't it? Okay. Now when I integrate this term, okay, integration of 1 by A plus L dA. This can be integrated by integration by substitution. A plus L can be taken as P. A plus L is taken as P. You already know integration by substitution, no? So dP by dA is equals to 1, or dP is equals to dA. So after I'll write dP by P. Integration of dP by P is nothing but ln P. Okay, and again substitute the value of P as A plus L. So you understood or you have learned integration. Okay, I have also shown you integration in mechanics. So the integration of this part would be nothing but ln A plus L. Okay, the integration of this part would be nothing but 1 by A dA is nothing but ln A. So the work done out here, work done is equals to nothing but G small m capital M by L into ln A plus L minus ln A. Okay, log A minus log B is nothing but log A by log B. Okay, so not log A by log B, log A by B. Log A minus log B is equals to log A by B. This is a property of logarithm that you know. Okay, so work done is equals to G small m capital M by L into ln A plus L divided by A. Okay, so this is our answer. Now to put out the limits, see, I've solved for integration fair and fine. Also to put out the limits, no? Okay, so the lower limit out here is nothing but infinity. Okay, work done in bringing a this mass from infinity to this distance A. So the initial point is infinity. The final point is distance A. Okay, and out here A plus L divided by A can be simplified as 1 plus L by A, isn't it? A plus L by A can be simplified as 1 plus L by A, isn't it? So out here work done is equals to G small m capital M by L into ln A 1 plus A by A. Okay, 1 plus L by L by A, 1 plus L by A. Okay, minus put the value of infinity out here at the place of A is nothing but this entire terms becomes ln 1, and the value of ln 1 is nothing but 0. So this entire terms becomes 0 minus 0. You put the value of infinity out here in place of A. This entire term becomes 1 plus L by infinity. L by infinity is nothing but 0. So 1 plus 0 is nothing but 1. ln 1 is nothing but 0. So this entire term is 0. So work done in bringing this mass from infinity to distance A is nothing but G small m capital M by L into ln 1 plus L by A. Understood this much? Okay. Now what is potential energy? Potential energy is nothing but negative of this value. So potential of this point or potential energy of the system is nothing but minus G small m capital M by L into ln 1 plus L by A. Okay, so this is the potential energy of a rod of length L separated at distance A. Okay, so this is our question. So in this question, we have to find out the angular momentum in an elliptical orbit. Okay, whenever there is some elliptical orbit, convert that elliptical orbit into a circular orbit, isn't it? But the radius of the circular orbit or the radius of the converted circular orbit is nothing but semi-major axis. Semi-major axis is nothing but minimum distance plus maximum distance divided by 2, isn't it? Minimum distance plus maximum distance divided by 2. That is nothing but the semi-major axis. And semi-major axis is nothing but the radius of converted elliptical orbit to a circular orbit. That is what I said up till now. So before solving this question, let me compare something. Okay, see, the derivation of elliptical orbit is little bit more complicated than you think. Okay, so I'll just give you the formula for ease of mnemonic. Okay, I'll just compare both. Okay, circular orbit and elliptical orbit. Elliptical orbit. Okay, circular orbit, elliptical orbit. Let's draw a line. Okay, okay. Let's draw a line. After that, in a circular orbit, okay, the center mass is m and a planet is rotating. Okay, out here in an elliptical orbit, the center mass is also m and the planet is rotating in this elliptical orbit. Okay. In an elliptical orbit, you need to know two things: r mean or minimum distance from the parent mass and r max. R max. Okay. And for elliptical orbit, you must convert this elliptical orbit into a circular orbit. Isn't this? But m, this planet is rotating, and the radius of circular orbit is nothing but semi-major axis. Semi-major axis is nothing but r minimum plus r maximum divided by 2. That means this minimum distance plus maximum distance divided by 2 is nothing but the semi-major axis. Now the first thing, okay, what is time period? See, time period for a circular orbit would be nothing but, recall the formula. What is the time period for a circular orbit? 4 pi r cube divided by g into mass of sun or g into mass of parent body. Similarly, so time period for a circular orbit is nothing but under root of 4 pi square r cube, where r is nothing but the radius of circular orbit. R cube by g into mass of parent body. Similarly, for elliptical orbit, time period would be nothing but t is equals to 4 pi square into a cube. Instead of using r cube, okay, I'll use a cube, where a is nothing but the average of minimum distance from the sun and maximum distance from the sun. This much is understood. This a out here is nothing but minimum distance from the sun plus maximum distance from the sun divided by 2, divided by g into mass of parent body. Then find 2. Okay, energy. Energy means total kinetic energy plus potential energy, or total kinetic energy plus potential energy of this orbit. Okay, or total mechanical energy of this orbit. Then fine. The total mechanical energy of this orbit is nothing but minus g mass of parent body into mass of this mass of rotating body divided by 2a, sorry, 2r. Okay, if you use or if you find out the total energy by using formulas, the first formula that you have to use is you have to find out velocity. Velocity is equals to gm by r. Okay, then find out kinetic energy. Okay, and the negative of kinetic energy is nothing but the total energy. Okay, I'll show you those all things different in later part of the video. Just now remember the total mechanical energy of this particle rotating in this orbit is nothing but minus g into mass of parent body into mass of rotating body divided by 2 into radius, isn't it? Okay, out here. Similarly, the total energy in an elliptical orbit would be nothing but minus g mass of parent body into mass of smaller body divided by 2 into a. Okay, the total energy out here is 2 into a. This is not potential energy or kinetic energy. This is total mechanical energy. That means addition of kinetic energy plus potential energy at each part of the orbit. Okay, that means total kinetic energy out here plus potential energy out here plus means total kinetic energy out here plus potential energy out here. Okay, this is the summation of total kinetic energy plus potential energy. Out here also this is the summation of total kinetic energy plus potential energy. Okay, and in a circular orbit, by intuition you can understand that the total kinetic energy in an in a circular orbit will remain constant. The potential energy will also remain constant. Okay, so the total mechanical energy will also remain constant at each part of the circular orbit. But in an elliptical orbit, the kinetic energy will vary for different parts of the ellipse. That means out here it will go very fast, out here it will go very slow, isn't it? So kinetic energy and potential energy would vary at different part of the ellipse. Okay, but the total mechanical energy, that means the total summation of kinetic energy plus potential energy, would remain constant throughout the entire orbit. That means kinetic energy plus potential energy out here would be equals to kinetic energy plus potential energy out here would be equals to kinetic energy plus potential energy out here, which is nothing but minus gm small m by 2a, isn't it? The third parameter, angular momentum. Okay, angular momentum in a circular orbit would be nothing but m into mass of rotating body or mass of orbiting body into under root of g mass of parent body into r. Okay, if you derive the formula, it will be this one. Similarly, okay, angular momentum in an elliptical orbit. See, angular momentum in a circular orbit also remain constant. Angular momentum in an elliptical orbit would also remain constant. The angular momentum is m into r into v, but I'll write those terms in terms of g, m, and radius. Okay, for a m into under root of g mass of sun into a. Okay, there is one more parameter out here. Okay, that derivation I'll give you later. But the only difference is in when you find out angular momentum in circular orbit, it will be this one. When you find out angular momentum in elliptical orbit, you have to multiply this a by one more term, and that is nothing but 1 minus e square. But e is nothing but eccentricity of the orbit. Eccentricity of orbit. Now, those of you that are asking, sir, why or how, I'll show you the derivation a little bit later. First, let me give you the formula so that you can easily relate. The total time period is equals to nothing but this one, this one. Total energy is equals to this one, this one. Total angular momentum is equals to this one and this one. Similarly, the velocity, okay, at each part of the orbit for a circular orbit is nothing but, how do you find out velocity? Velocity is nothing but or magnitude of velocity. See, the vector of velocity in a circular orbit will vary. The magnitude of velocity is nothing but angular momentum divided by radius. No, see, if I say angular momentum is equals to m into r into v, okay, and sine alpha. Alpha is nothing but the angle between r and v. Then circular orbit, the angle between r and v is always 90. So this sine alpha always becomes 1. Okay. So if I find out the angular momentum, m into g under root of gmr, angular momentum, and divide the angular momentum by mass into radius, can I find out the velocity? So velocity is nothing but angular momentum divided by mass into radius. So angular momentum divided by mass into radius. Velocity out here, if you see this equation, velocity out here is nothing but angular momentum divided by mass into radius out here. So angular momentum is nothing but capital M into gmr divided by mass into radius. Okay, you can cancel out the mass, and if you want to put out, this is nothing but gm r by r square. So out here you can cancel out the r. So orbital velocity is nothing but under root of gm by r. Okay, we have also done this one, under root of gm by r. Gm by r. Okay, similar kind of thing if I do out here in an elliptical orbit. However, the angle between r vector and v vector is not always 90 degree. Okay, so the term of sine alpha will always come out here. That means you always have to find out the angle between r vector and v vector. Without that, you cannot find out the velocity at each point. Okay, so if I follow the similar kind of approach, velocity is nothing but angular momentum divided by mr. So angular momentum in an elliptical orbit is nothing but g into ma 1 minus e square, isn't it? Okay. However, in an elliptical orbit, I have to divide by m into r into sine alpha, because in an elliptical orbit, the value of sine alpha is not always 90, or this value of alpha is not always 90. So sine alpha will not always be 1. Okay. So I have to, in order to find out the velocity, I have to divide angular momentum by m into r into sine alpha. Okay. Divided by mr sine alpha. Mr sine alpha is nothing but the eccentricity of the elliptical orbit. Fair and fine. Is there any other thing that I need to calculate? See, potential energy you can already calculate by gm by r. Okay, you do not need a special formula for that. Kinetic energy, if you find out the velocity, okay, or instead, see, the total mechanical energy will always remain constant, no? Okay, total mechanical energy throughout the elliptical orbit will always remain constant. So if you can find out the potential energy, okay, can you find out the kinetic energy from that formula? Obviously, you can find out the kinetic energy. Suppose I have to find out the kinetic energy at this point. I know that total energy is nothing but minus gm by 2m. The kinetic energy out here is nothing but potential energy, or minus gm by r, isn't it? Minus g capital M small m by r plus x, that is nothing but the kinetic energy, is equals to total energy. Okay, so remember these all formulas. Okay, understood this much? Okay, so having said these all things, now let me derive. See, up till now I have said convert the elliptical orbit into a circular orbit. Okay, but the actual derivation is little bit tedious, and you have to just look through the derivation, then we'll discuss them. Okay, but make sure to remember this formula. These formulas are for the ease of memorization. Okay, that's why I said convert the elliptical orbit into a circular orbit. Understood? Now, using the formulas before, okay, now this is the formula that I have shown you for angular momentum in an elliptical orbit. isn't it? I'll just derive this formula. Okay, I have to find out the angular momentum in an elliptical orbit. So suppose this is an elliptical orbit, fair and fine. This is the mass of sun. Okay, this is minimum radius, this is maximum radius. So instead of using r mean and r max, I'll use r1 and r2 because it will get very complicated. Okay, r1 is nothing but minimum radius or minimum distance from the parent body or minimum distance from the sun. R2 is nothing but maximum distance from the sun. What do I know about elliptical orbits? There are two theorems that we'll use for this derivation. The first theorem is angular momentum throughout the orbit remain constant. Angular momentum throughout always remains constant. Okay, always remains constant. The second one is the total energy in this elliptical orbit will always remain constant. Okay, why does the angular momentum remain constant? Because the torque is always zero at every point in the orbit. And why is the total energy always remain constant? Because the only force that is acting on this orbiting body is nothing but gravitational force. And gravitational force is conservative in nature. So whatever kinetic energy is reduced, that will be converted into potential energy of the planet. Understood? Okay. So the total mechanical energy in this elliptical orbit will always remain constant. Okay. Total mechanical energy will always remain constant. Okay. Now there are two parameters that are given, R1 and R2. And do you know why are these two parameters given? Because using R1 and R2, you can find out the value of a same major axis. The second part is at this point in R1, the velocity would be perpendicular to R1 vector. And at this point R2, the velocity would also be perpendicular to R2. Okay, let the velocity at R1 be V1, let the velocity at R2 be V2. So velocity out here is perpendicular, velocity out here is also perpendicular. So when I use the formula for angular momentum, A mark is sine alpha, the value of alpha is 90. Okay, so when I'm using the first formula, angular momentum, AM into R cross V into sine alpha. The value of sine alpha out here is 90. The value of sine alpha out here would be also 90. So it is nothing but AM into R1 into V1 into sine 90. I'm not writing sine 90 is equals to 1. Okay, which should be equals to AM into R2 into V2. AM into R2 into V2. Why? Because the angular momentum of the particle out here is equals to angular momentum of the particle out here. Fair and fine. Now point number 2. What is the total mechanical energy out here? The total mechanical energy out here is nothing but kinetic energy plus potential energy. Okay. So kinetic energy is nothing but half m v1 square plus what is the potential energy out here? Minus g m into small m minus g capital M into small m divided by r1, isn't it? Which should be equals to what is the total kinetic energy out here? Half m v2 square. What is the total potential energy out here? Minus g capital M into small m into divided by r2. Minus g into capital M into small m divided by r2. Now let me send this term to the left hand side and this term to the right hand side. Okay, or half m v1 square minus half m v2 square is equals to g capital M small m by r1 minus g capital M small m by r2. Okay, I can cancel out the m from all the parameters. Okay, it doesn't make a difference. Just cancel it out. Okay, now take half common from left hand side. The rest part is nothing but equation solving. V1 square minus V2 square is equals to Gm. Take Gm common. 1 by R1 minus 1 by R2. Okay. Now using these two formulas or using these two equations, equation number 1 and equation number 2, I'll find out the angular momentum. Okay. Angular momentum. So out here I'll just substitute. First part is I have to find out velocity. Then from velocity I'll substitute back into m and v. Okay. So to find out velocity or v1, let me just substitute v2 out here. Okay. R1 v1 is equals to R2 v2. From this equation I can get R1 v1 is equals to R2 v2 or R1 v1 by R2 is equals to v2. Okay. So v2 is equals to nothing but R1 into v1 divided by R2. So if I substitute the value of v2 out here, okay, I'm substituting the value of v2 out here. What do I get? R1 v1 by, I'm substituting the value of v2 out here, or R1 v1 by R2 whole square. No, okay. So I'll just copy this equation on the next page. Let me just copy this equation. and then I'll solve it. Okay, copy the equation and solve it. Let's take the equation top. Okay, so I'll just solve the equation very quickly. Okay, half into v1 square minus r1 square v1 square divided by r2 square. Okay, is equals to gm 1 by r1 minus 1 by r2. Okay, or half v1 square, I'm taking v1 square common, 1 minus r1 square by r2 square is equals to gm 1 by r1 minus 1 by r2. Okay, okay, out here what can I do? I can do out here r2 square minus r1 square. Okay, or half v1 square is equals to r2 square minus r1 square divided by r2 square is equals to gm r2 minus r1 divided by r2 r1. Okay, now r2 and this square root get cancelled. Okay, r2 square minus r1 square can be written as r2 plus 1, sorry, r2 plus r1 into r2 minus r1, a minus b, or a square minus b square. This term is nothing but a square minus b square, no? So one of the term would get cancelled. So a plus b into a minus b. So this term would be r2 minus r1 into r2 plus r1. This term, okay, this r2 square minus r1 square, I've written it out here. Okay, so this term I've written it out here, this top term only. Now r2 minus r1 and r2 minus r1 would get cancelled. Okay, so we're left with half v1 square into r2 plus r1 divided by r2 is equals to gm by r1. Okay, fair and fine. What do I need to find out? I need to find out the velocity. Or v1 square is equals to 2 gm by r1. Okay, 2 gm by r1 into r2 by r2 plus r1. Okay, on v1 is equals to under root of 2 gm by r2 plus r1 into r2 by r1. Okay, this is my velocity. Now what do I need to find out? I need to find out the angular momentum. Okay, I have found out the velocity. See out here, I have found out the velocity at v2. What did I find out? I found out the value of v1. Sorry, I found out the value of v1. So I found out the value of velocity of the planet or velocity of the orbiting body out here. Okay, now can I apply angular momentum is equals to m1 r1 into v1, and m1 r1 v1 is equals to m2 r2 v2. So angular momentum at every point in the orbit would be same, and that value of angular momentum is nothing but m1 r1 into v1. And I have already found out the value of v1. So the value of angular momentum is equals to m r1 v1. The value of v1 I substitute from out here. Okay, so angular momentum is nothing but am into r1 into what is the value of v1? 2 gm by this entire thing. 2 gm by r2 plus r1 into r2 divided by r1. And if I send this r1 inside the square root, what will happen? It will become square. So I'm sending this r1 inside the square root. So square and r1 got cancelled. So our angular momentum is nothing but am into under root of 2 gm by r2 plus r1 into r2 r1. Okay, this is our formula for angular momentum. This is our formula for angular momentum. Now you might ask, sir, you have told us a different formula for angular momentum. This is not the formula that you told us. See, I haven't told you this formula. No, I told you a much simpler formula. Sir, what is this? This parameter and this parameter are the same thing. I'll show you how. Okay. Okay. What did I say? Achha. Let's add one more slide. Okay, so that it will be easier to understand. Okay. I'm comparing this value. Okay, this value. Let me just copy it. I'll compare this value of angular momentum that I have derived to the value of angular momentum that I told you to memorize. Okay. Now here also there is important concept out here. Okay. How is this two related? Okay. This is nothing but 1 minus c square. This is r2 r1. See out here. In an ellipse, minimum distance is nothing but r1. Maximum distance is nothing but r2 as given in irodov. You can use r mean and r max, okay, in the situation present itself. Understood this much? Okay. Now see, this r2 plus r1 divided by 2, these two can be taken down out here, no? These two can be taken down out here, isn't it? The 2 out here can be divided out here. And what is r1 plus r2 divided by 2? R1 plus R2 divided by 2 is nothing but A, isn't it? Same major axis. So R1 plus R2 divided by 2 is nothing also but same major axis. So this much is simple. Okay, R2 plus R1 divided by 2 is same major axis. What about this R2 and R1? Now remember, okay, I've told you something about eccentricity. Eccentricity is nothing but distance from the center to focus divided by same major axis. Okay, and semi or major axis is nothing but 2A. Minor axis is nothing but 2B, isn't it? So major axis is nothing but 2A, minor axis is nothing but 2B. This much is understood. Okay. If this much is understood, can I say there is a formula for ellipse? Formula of ellipse. Okay. Let's see the ellipse out here. Okay. This is the center of the ellipse. Okay. Center. This is the focus of the ellipse where our planet is located. This distance is R1. The larger distance is R2. Okay. The larger distance is R2. Okay. This distance is nothing but semi-major axis. Okay. And eccentricity is nothing but this distance. Okay. Achha, origin. Let me write center as origin. Okay, otherwise you'll get confused. This distance, let me term as C. So eccentricity of an orbit is known as C by A. Fair and fine. Now can I write R1 in terms of eccentricity and A? See, R1 is equals to A minus C. R1 is equals to A minus C. Okay. And C can be written as E into A. C can be written as E into A. So if I substitute the value of C out here, R1 can be written as A minus EA. Okay. Or R1 can be written as A into 1 minus E. Similarly, R2. This distance is R2. Okay. This larger distance is R2. Can I say R2 as C plus A? R2 is equals to A plus C. Or R2 is equals to A plus E into A. Or R2 is equals to A into 1 plus E. So R1 is equals to A into 1 minus E, R2 is equals to A into 1 plus E. So just substitute the value. Okay. So angular momentum is equals to AM into under root of GM by A into R2. What is the value of R2? A into 1 plus E. A into 1 plus E. What is the value of R1? A into 1 minus E. A into, or let's say A into 1 minus E. A into 1 minus E. Let's cancel one of the E. So I'll get angular momentum is equals to AM into under root of GM. One of the A is remaining out here. Okay. A 1 plus E into 1 minus E can be written as 1 minus E square or 1 minus E square. Okay. And this is the same formula that I've shown you before. Nothing different. Okay. Okay. So I derived angular momentum. Okay. But how do I derive time period? See, the derivation of time period, just see it once. Okay. Time period, I've just shown you a trick, no, convert the elliptical orbit into a circular orbit. But what is the actual derivation? And note one thing: the actual derivation is nowhere in your, is not there in your net. Okay. It was there in a journal. I have to see it. The derivation is actually very easy. Okay. It uses your class 12 concepts and it is inside your syllabus. However, things that are not given. Okay. Inside your syllabus means the question can be asked. Nothing in the derivation will be outside your syllabus. Okay. It's just the fundamental understanding of fundamental concepts. Okay. How do you understand the fundamental concepts? So what I'm trying to do is I'm trying to derive the time period, that is 4 pi a cube by gm. So let me derive the time period. Time period of an elliptical orbit. Elliptical orbit. Meow, 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 meow. So this is the elliptical orbit. Okay. And this is our center mass. Okay. Okay. Now we have to use something called angular momentum. Okay. See, angular momentum, or the derivation of angular momentum is already done. No? See, the derivation of angular momentum I've done out here. Okay, I've used, sorry, but I used two parameters: conservation of total or conservation of angular momentum, conservation of mechanical energy. And using these two parameters, I have derived the angular momentum in an elliptical orbit. Okay, where angular momentum is nothing but m into gma 1 minus e square. So angular momentum I already know. There's no trick out here. Okay, m into under root of gma 1 minus e square. See, okay, the fundamentals are very easy. Okay, okay. What do I need to find out? I need to find out the total time taken for a elliptical orbit. How? Kepler's second law. What does Kepler's second law say us? Kepler's second law says us a planet covers equal areas in equal time. Equal time. See, you have done Kepler's second law inside the class, and you fairly have an understanding of animation of Kepler's second law. That means if the time taken by Earth to move from head to head, the time taken by Earth from head to head is 1 second. Okay, the Earth is orbiting around the Sun in an elliptical orbit. But when the Earth is out here, I've started my stopwatch. When the Earth went out here, I stopped my stopwatch. Okay, the time taken for Earth to travel from head to head is 1 second. Okay, or 2 seconds, or whatever time is it. Let's say 1 second. Okay, so if I shade this area, when the particle or when the Earth goes near the Sun, it will travel much faster. Okay, so similarly, time taken by Earth to cover from head to head is also 1 second. 1 second. Okay, time taken by Earth to cover from this position to this position is also 1 second in the elliptical orbit. What Kepler says is that this area, this shaded area, is equals to this shaded area. Okay, if this area is A, this shaded area is A, that means this shaded area is also A. Okay, this shaded area is also A. Fair and fine. I understood Kepler's law. But how do I convert Kepler's law into Newtonian mechanics? How? Okay, just make this area a little bit small. Okay, see, I'm drawing. Understand this parameter very carefully. This is the parent out here. This is the area. Okay, I'm trying to find it out. This is the velocity out here. Okay, and this area or the time that I'm taking is very small. Okay, just for the ease of understanding, I've drawn this area a little bit bigger. Okay, fair and fine. Okay, now what is the formula of this area in Newtonian mechanics? Okay, this is r vector. Out here is r vector. This much is r vector. This is v vector. What is the formula of this area in Newtonian mechanics? Let's say this particle travel for dt time. Okay, this velocity or Earth traveling with velocity v for dt time. So the total distance out here would be v into dt. So r is out here. The total distance traveled in dt time is nothing but v into dt. Okay, distance traveled in vt time. Total distance traveled in time dt is equals to velocity into time v dt. Okay, so total distance traveled is equals to v dt. Now I must find out this area or this much area. Okay, how do I find it out? Okay, what happens if I do r cross v dt? Now understand, this applies a concept of cross product of vectors. Okay, what is r cross vdt? R cross vdt. R cross vdt is nothing but the area of parallelogram. No, the area of this parallelogram is nothing but r cross vdt, isn't it? If I do r cross vdt, it is nothing but the area of the entire parallelogram, isn't it? Understood? So what is the area of this much shaded area, or what is this much shaded area? Half of the area of parallelogram. So the shaded area is nothing but half of the area of parallelogram. The concept out here was vector cross product. That means if you're crossing A cross B, it is nothing but area of a parallelogram of A vector and B vector made by A vector and B vector. Understood? So this much area is nothing but R cross VDT divided by 2. It is the area. This is nothing but area covered in time dt. Isn't it? area covered in time dt, isn't it? This much area is covered in time dt, no? Okay, so area is nothing but, or r cross v by 2 is equals to area. Okay, v dt, sorry. Now can I send this dt down out here? I can send this dt down out here, dt. Now if you look very carefully, this became just dA by dt, isn't it? This entire area by dt became dA by dt. This much is understood. Did you understand this one? V dt, dA by dt is nothing but r cross v by 2. Because r cross v dt is nothing but area of parallelogram, and the area traveled is nothing but half of the area of the parallelogram. Or area covered in time dt is nothing but half of the area of parallelogram. Now if I send this dt down out here, dA by dt is nothing but r cross v by 2. This was the main fundamental concept that you have to understand. Remaining part is simple. When did you see r cross v? If I add or if I multiply, okay, r cross v, sorry, let me take this parameter. Now the remaining part is simple. Playing with just algebra. R cross v by 2 is equals to dA by dt. Multiply the numerator by scalar quantity, multiply the denominator by scalar quantity. M into r cross v. What is M into r cross v? Angular momentum by 2m is equals to dA by dt. Understood this one? Okay. dA by dt is nothing but angular momentum divided by 2m, and angular momentum throughout the entire orbit remain constant. Okay. Now the second concept that you have to understand is, if I give out the total area of this ellipse, okay, if I give out the total area of the ellipse, can I find out the time? Okay, area of ellipse, this out here, if I substitute out here, area of ellipse, and out here, time taken to cover that area, time period, isn't it? Okay, area of ellipse, time period. Now area of ellipse is nothing but area of ELLI PAC. Ellipse is nothing but pi AB, pi into AB. This should be known. Okay, the time period I'm using as t. Okay, so my simplified equation becomes L by 2m is nothing but area, or pi a into b by t. Okay, now I just need to find out the value of t. T is equals to nothing but L by 2m divided by pi a b. There is one more concept. In our original formula, there was no parameter of b. See, there was no parameter of b. I'm just using a. So out here, a parameter of b came out. Okay, there is another formula for ellipse. Okay, equation of ellipse. Let me do everything on the same page so you do not get confused. Okay, there's another equation of ellipse, or another concept of ellipse. B square by a square is equals to 1 minus e square. From where does this formula come? This is a mathematical formula for a ellipse. Okay, b square by a square is equals to 1 minus e square. That means semi-major axis square divided by semi-minor axis square is equals to 1 minus eccentricity square. This is a formula for ellipse. Okay, this is a equation for ellipse. So b square divided by a square is nothing but 1 minus e square. From this formula, I'll substitute the value of b. Okay, now angular momentum by 2m is nothing but pi into a into, what is the value of b? Value of b is nothing but under root of a square into 1 minus e square. Under root of a square into 1 minus, it's getting very cluttered. Okay, so let's solve this. You understood the parameters. All the formulas that I'm using out here are already in the book, are already in this slide. Sorry, this formula is not anywhere in the thing. Okay, but the concept that I used out here is inside your class 12. No? You do not need advanced mechanics or numerical methods. Okay, everything that you understood is from class 12 only. No? Is there any other formulas that I used? Area of an ellipse, you have to know. This one you have to know. This one will be taught in class 12. Okay, so there are three formulas. dA by dt is nothing but r cross v by 2. And how did you get that? You understood this one. Okay, b square by a square is nothing but 1 minus e square. Understood? And third one is this one. M into r cross v is nothing but angular momentum. Okay, so I'll just copy this formula. L by 2m is equals to pi ab by t. So let me just add a new slide. I'll just copy this formula. Okay, L by 2m is equals to pi ab by t. So L by 2m is equals to pi ab by t, where pi ab is nothing but area of the ellipse. And what I'm using to substitute b square by a square is equals to 1 minus e square. This is the standard equation of ellipse, not equation of ellipse. This is the standard notation in ellipse. Okay, so b square divided by a square is equals to 1 minus e square. So let me just write it fast. Pi a, I'm substituting the value of b. Okay, or b is equals to under root of a square 1 minus e square by t. Okay, what is the value of angular momentum? The value of angular momentum is nothing but under root of, or m into under root of g capital M a into 1 minus e square, where I've already shown you y2m is equals to pi a square into 1 minus e square, okay, divided by t. Now if you divide 1 minus e square and 1 minus e square will get cancelled, m and m would get cancelled. Okay, acha out here. Okay, let me simplify. Just m got cancelled, 1 minus e square and 1 minus e square got cancelled. Okay, this a into under root of a square is nothing but a square. So this entire thing would become a, and a into a is nothing but a square. Okay, now if I send this a square out here, pi a square, I'm sending this entire pi a square down out here. Okay, our time period is equals to, just sending the time period out here, cross multiplying. The time period is equals to 2 pi a square by under root of g into m into a, g into m into a. And t is equals to, let me write this also, under root 4 pi square a to the power 4 divided by g into m into a. Okay, a square, and it will become a cube. Time period is equals to 4 pi square a cube divided by g into m. Okay, now this is the part that your teacher skips. Okay, and that's why in order to remember the trick, I said convert the elliptical orbit into a circular orbit, because if you go through the entire derivation, it will be very lengthy, no? So that convert the elliptical orbit into a circular orbit is just a trick to remember the time period, energy, and things. In this question, we have to derive the total energy. Okay, so the question is very stupid. Okay, using conservation laws, demonstrate that the total mechanical energy of a planet M moving around the sun in an ellipse only depends upon its major axis. Okay, find this energy as a function of A. The total energy will always remain constant. No? Why? Because only one force is acting, and that is nothing but the gravitational force, which is a conservative force. So whatever is the mechanical energy, that will always remain constant. The part of the question that is been asked out here is you have to derive this formula. Okay, a total energy in an orbit or in an elliptical orbit is nothing but minus g into capital M small m divided by 2a. Okay, the jugaad I have already said you. The jugaad is same as convert. So the actual derivation is the different. Okay, how different? In the previous problem, I have found out the velocity v1 at topmost point. Okay, v1 at topmost point is nothing but how much? This value, isn't it? v1 at topmost point is this value, and if I multiply half into m by v1, I'll get the kinetic energy at topmost point. Okay, and if I if I add the potential energy at topmost point, what is the potential energy at topmost point? Minus g into m into r1 divided by r1, isn't it? So if I add kinetic energy plus potential energy out here, I'll get the total mechanical energy. So that is the only thing that I have to do. So total mechanical energy is equals to kinetic energy plus potential energy. Kinetic energy is nothing but half m v1 square. Okay, what is the value of v1 square? What is the value of v1 square? v1 square is nothing but 2 gm divided by, acha, let me write in terms of a, gm by a into r2 by r1. Okay, let me just write this in terms of a. Okay, it will be easier for me. v1 is equals to gm by a into r2 by r1. So v1 is equals to under root of gm by a into r2 by r1. I'll tell you one more additional information. v2 is nothing but the velocity at bottommost point. v2. Okay, v2 is nothing but just inverse this one. Same thing, gm by a into r1 by r2. Okay, so velocity at topmost point is gm by a r2 by r1. Velocity at bottommost point is gm by a r1 by r2. Nearest point, farthest point. Velocity at nearest point, velocity at farthest point. So kinetic energy is equals to half m v1 square, or this square is nothing but gm by a into r2 by r1, isn't it? Potential energy is nothing but minus g capital M small m divided by how much? r1. Potential energy at point 1 is nothing but minus gm capital M small m divided by r1. No, See, potential energy at nearest point minus G capital M small m divided by R1, isn't it? Okay. So potential energy, I found out kinetic energy, I found out total energy. So total energy T is nothing but half m Gm by A into R2 by R1 minus Gm by R1. Now I'll convert R2 and R1 in terms of A. Okay. In elliptical orbit, R2 can be written as, where is R2? Where is R2? See, I've already shown you, but see, R2 can be written as A into 1 plus C. R1 can be written as A into 1 minus C. I have already shown you this one. Where have I shown you this one? See, this is the problem. Okay, R2 by R1 derivation. See, R1 and R2. R2 is equals to A into 1 plus C. R1 is equals to A into 1 minus C. Okay. So R2 is equals to this value A into 1 plus C. R1 is equals to A into 1 minus C. Okay. So convert everything. Total energy is equals to half m Gm by A. Why Gm by A? Because R1 plus R2 divided by out here. R1 plus R2 divided by 2 was nothing but A, same major axis. Okay. Into R2. R2 is nothing but A into 1 plus E. R1 A into 1 minus E minus Gm by G capital M small m. Out here small m. Don't forget the small m. Divided by R1 A into 1 minus E. Okay. Cancel this A out here. Okay. Let's cancel the A. Okay. If I'm to take LCM. Okay. After taking LCM, I'll get, or I'll just A into 1 minus C. I'm taking A into 1 minus C common from the denominator. Okay, I'll be left with half mg capital M minus into 1 plus E minus how much? Gm small, this one. Okay, I can take G capital M small m common also, isn't it? I can take it outside. So G capital M small m. I'm taking G capital M small m common minus 1. Okay, so 1 plus E by 2 minus 1. 1 plus E by 2 minus 1. So 1 plus E by 2 minus 1, isn't it? Okay, this is nothing but G. Okay, now let's take LCM. If I take LCM, 1 plus E, take LCM 2 minus 2. So it would be nothing but minus, it would be E minus 1. So this plus 1 and minus 2 becomes minus 1. So it would be E minus 1 by 2. So this entire thing, 1 plus E divided by 2 is nothing but E minus 1 divided by 2. E minus 1 divided by 2. Now E minus 1, I can write E minus and 1 as minus 1 into 1 minus E plus 1. That means what? I'm multiplying this entire thing by negative. Minus 1 into 1 minus E is nothing but E minus 1. This 1 minus E and this 1 minus E will get cancelled. Okay? Okay? And our energy becomes minus G capital M small m divided by 2. So this is our energy, a total mechanical energy in the orbit. So energy is equals to minus G capital M small m divided by 2. See, G capital M small m divided by 2. See, G capital M small m divided by 2. Okay. So this is the formula that you must remember. The shortcut to remember the formula is convert elliptical orbit into circular orbit. Okay. In angular momentum, there is another parameter of 1 minus E square that you have to remember, and velocity becomes somewhat this one. Okay. So this is the formula that you must remember. The derivation or the actual derivation instead of using shortcut, okay, is the thing that I have shown you out here.